In this recording, we're going to go over some motor controls problems having to do with transformers, three-phase circuits, and magnetic circuits. Okay, so let's start off. The first problem we're going to do, we have a 1000 volt amp, 230, 115 volt transformer. And on this transformer, we did an open circuit and a short circuit test so that we could get the parameters of the equivalent circuit. And here are the results. So for the open circuit test, the open circuit voltage was 115 volts. The current was 0.11 amps. And the power was 3.9 watts. For the short circuit test, we had a short circuit voltage that was 17.1 volts. A short circuit current of 8.7 amps. And a power of 38.1 watts. And what we are asked for here, we want to find the equivalent circuit. We're going to refer that to the low voltage side. Then we're going to find the voltage regulation at 0.8 power factor lagging. And we'll determine the efficiency at that condition as well. So the voltage regulation and the efficiency at 0.8 power factor. Okay. So first we will deal with the results of the open circuit test. And we can compute the magnitude of the excitation admittance, which is equal to, and remember we're working on the excitation branch here, which is a parallel branch, so we're going to work in terms of conductances and admittances. Okay, so this is 0.11 amps over 115 volts. Essentially, this is Ohm's law. If we do this division, we get 0.009565 Siemens. Okay. So that gives us the magnitude of the excitation branch admittance. And now we just need the angle. So to find that angle, the equation that we need is that the angle theta, we're going to use the power here, is the inverse cosine of the open circuit power divided by the open circuit voltage times the open circuit current. And this is inverse cosine of 3.9 watts. That was given in the problem. And we know that the open circuit voltage was 115 volts times the current was 0.11 amps. And if we compute that, we end up with 72 degrees. So the excitation branch admittance is equal to 0.00, I think I missed a 0 up here, 0.9565 at an angle of 72 degrees. And if we want to convert that to rectangular coordinates to get in this form, we would just use trigonometry to get this. We get 0.0002956 minus j 0.0009096. And then to get the resistance, that of course is equal to 1 over, we'll call this G sub C, which is 3383 ohms. And X sub M equal to 1 over B sub M is 1099 ohms. So we get all that from the open circuit test. Now let's move on to the results of the short circuit test. So in the short circuit test, we find that Z equivalent, the equivalent impedance, which is going to be equal to R equivalent plus JX equivalent. We're using the simplified circuit model here. This is going to be equal to 17.1 volts. These come from the results of the short circuit test divided by 8.7 amps. And that gives us 1.97 ohms. And to find the angle, similar idea here. It's going to be the inverse cosine of the power over the voltage times the current. In this case, the power was 38.1 watts times 17.1, or divided by 17.1 times 8.7. And that gives us 75.2 degrees. An inverse cosine here. Okay. And then, so I have 1.97 at an angle of 75.2, and if I want to convert that to rectangular coordinates, it turns out to be 0.503 plus J 1.905 ohms, so R equivalent is 0.503 ohms, and X equivalent is equal to J 1.905 ohms. I guess that J technically shouldn't be there. Okay, so at the end of the day, my circuit looks like this. Okay, and this is R equivalent, this is JX equivalent, and IS flowing out in that direction, IP, This is VP over A. This is actually A times IP. We're referring. So this is R sub C over A squared, and this is JX sub M over A squared, V sub S. And that's our equivalent circuit, where these values are all the ones that we found up above. Okay, so that gives us our equivalent circuit, and now we want to find the voltage regulation. We're going to use this equivalent circuit to find that voltage regulation. And we're going to do that at 0.8 power factor lagging. So at 0.8 power factor lagging, we have VP prime is equal to, we're using the equivalent circuit for this. Is equal to VS plus Z equivalent IS. This is just Kirchhoff's voltage law. And this is equal to 115 at an angle of 0. Plus 0.126 plus J 0.476 times 8.7 at an angle of minus 36.87. So we crank through all of this and we find that VP prime is 118.4 at an angle of 1.3 degrees volts. Okay, this is just KVL in the equivalent circuit. And now to find the voltage regulation, that is going to be equal to 118.4 minus 115 divided by 115 times 100%. And this gives us a voltage regulation of 2.96%. Now, at rated conditions at 0.8 power factor lagging, the output power, P out, equal to VSIS cosine theta this is 115 times 8.7 amps times 0.8, and this gives us 800 watts. We get the copper losses. That would be equal to I squared R equivalent which is going to be 8.7 squared. And our equivalent is 0.126 ohms. So that gives us 9.5 watts. Our core losses is, we can compute that by doing Vp prime squared over R sub C. And that's 118.4 squared divided by 38 or 3383. And this gives us 4.1 watts. So the efficiency which is equal to P out over P out plus the copper losses plus the core losses. This sum in the denominator here is Pn, which is broken down into three parts. So this is 800 divided by 800 plus 9.5 plus 4.1 times 100%. So this gives me an efficiency of 98.3%. For the next problem, let's consider that we have a delta connected load and we're given this voltage of 280, and we're also given that each phase of the load has an impedance of 3 plus J4 ohms. And so this is a 208 volt power line that we're tied to here, and we want to find the phase current and the line current. So here's IL, and here is an example of one of the phase currents. This is 208. Okay, so since this is delta connected, we know that the line voltage is equal to the phase voltage, and that is equal to 208 volts in this case. And just as a point of reference, our phase impedance, 3 plus J4, if we convert that, that becomes 5 at an angle of 36.87. Okay, so now we can compute I phase. I phase is equal to V phase over C phase. So that's 208 divided by 5 at an angle of 36.87. So this turns out to be 41.6 amps at an angle of minus 36.87. To find the line current, for the delta connected circuit, the relationship between the phase and the line currents is that it is by root 3. So the magnitude of the line current is equal to root 3 times the magnitude of the phase current. So that's just root 3 times 41.6 which is 72.05 amps. Okay. Problem you're going to see on the exam is going to have a a Y-connected source on this side, but a delta-connected load just like you see here. So this example should help you with your exam problem. All right, for the next problem, we're going to work with a magnetic core. And we have some windings on this core. Windings go around the core 200 times. The area of the core is equal to 12 centimeters squared. And the mean path lengths that we will deal with here, this first main one that goes around most of the core, that length is 50 centimeters. And then we kind of have this like a rotor idea here. So this length for this rotor, which is also ferromagnetic, is going to be 5 centimeters. And then we have a gap. The gap in between, kind of like this stator idea and this rotor idea. So the gap length is 0.05 centimeters. And we are going to have a relative permeability of 2000. And we are going to have a current in the coil of 1 amp. We want to find the flux density in the air gaps. And we're given that the cross-sectional area of the air gaps is 14 centimeters squared each, and that includes fringing. Okay. So the first thing we need to do is compute all the reluctances. This large piece here, we're going to call this the stator. This is kind of like a motor idea here. So R sub S is the reluctance of the stator, and that's equal to L sub S divided by mu R, mu naught A sub S. We can plug in the numbers for there. 0.50 meters. Remember, we have to convert to meters. Mu R is 2000 times 4 pi times 10 to the minus 7, which is mu naught, times 0.0012 meters squared. Remember, we're converting to meters and meters squared. And this turns out to be 166,000 ampere turns per Weber. Next, we'll do the rotor, that round piece. So that's going to be L sub R over mu R, mu naught, A sub R. So that's going to be 0.05 meters. That's the length of the rotor. We once again have a relative permeability of 2000 times mu naught. And our area, once again, 0.0012 meters squared. And this gives us 16,600 ampere turns per Weber. Finally, we have the air gaps. R sub A, L sub A over mu R, mu naught A. And this is going to be, the length is 0.005 meters. It's 3 zeros, meters. Mu relative is 1 because it's air, times 4 pi times 10 to the minus 7, times the area, which was given with fringing to be 0.0014 meters squared. Okay, so this comes out to be 284,000 ampere turns per Weber. Now, the magnetomotive force is equal to the number of turns times the current. We have 200 turns times 1 amp. So our magnetomotive force is 200 ampere turns. Our total reluctance is equal to R sub S plus R sub R plus R sub A, and that comes out to be 751,000 ampere turns per Weber. So the flux is 200 ampere turns over 751,000 ampere turns per Weber, and this gives us 0.000266 Webers. So that's our flux. Now we're concerned with our flux density. Which is our flux divided by our area. So this is 0.000266 Webers divided by 0.004 or 0014 meters squared, the area in our air gap. And so that comes out to be 0.19 Teslas. Okay, there's one more problem on the exam, and I'm going to just give you a hint at that. In the class where we did the equivalent circuits for the generators, we did a problem where we looked at the losses in a transmission line when we step the voltage up, send power down the transmission line, and then step it back down again so that it can service the load. You're essentially going to do that problem just with different numbers. So make sure you understand that problem from that lecture. Okay, if you have any questions, email me. Let me know right away if there's any of these problems that you think you're going to have an issue with. If you can do these problems, you should be fine for the exam. Good luck.